slices that will be your domain for your computation. So you have an initial slice of a space-like slice of constant time. You put your data on there. It solves what's called the constraint equation. So it's a solution of the Einstein equations induced on that surface. And then evolution equations are around the other part of the Einstein equations that tells you how this data propagates through time. So we did this with the plane gravitational waves in the lab yesterday, which was the only sort of simplification to that system was plane symmetry. So unlike the linear gravitational waves that Jörg explained, where you get these nice two polarization modes and so on, and you can do all of this analytically, these ones are completely nonlinear. They contain what's called back reaction, and so they can, in particular, self-interact. We have that nonlinear interaction going on, so, which makes it already quite interesting, even though it's quite a small system. Okay, so just to recap, we discretized our grid into a finite number of points. On those points, we wanted to compute spatial derivatives in order to evaluate the evolution equations to get off our initial surface. And we could do that by using finite difference operators. So we can approximate the derivative at a point by looking at the function evaluated at neighboring points. And we can do certain things near the boundaries to make sure that we don't overreach outside of our computational domain. Once we have the ability to approximate spatial derivatives on a given slice, we can evolve with evolution equations where the right-hand side can, given initial data, the right-hand side is completely intrinsic to a slice, so it can be evaluated numerically by the approximation methods for the spatial derivatives at least. And we can find that the right-hand side just turns into a sequence or a set of numbers corresponding to each grid point, at which point we can do something like Euler or Runge-Kutta to evolve that from t equals 0, for example, to t equals 0 plus a small step. And that is essentially the process. Once we then have the next slice, we can then take that data, do the compute the approximate spatial derivatives, so on, plug it into the evolution equations again, and then continue. So that's the main sort of process of these numerical relativity simulations. There was one thing that I left out in the numerical section yesterday that I wanted to just briefly mention, which was the CFL condition. This is extremely important for numerical simulations that describe propagation, because it is inherently related to stability. So basically the idea is that within one time step, so you go from surface 0 to surface 1, you don't want your information or your fields that are propagating along in a spatial direction, or with respect to the grid, you don't want them to be going further than one grid point within that one time step. So that is extremely important for stability. And in the lab today, you'll be playing around with the CFL number to see what difference it makes to the stability of your simulation. So a simple example is you have a 1D advection equation here, and where A, you might know this from partial differential equations in third year, that you do a characteristic analysis on this, and you find that A is in fact the speed of the propagation of U. And so what you want is you want that this CFL condition holds, knowing that A is your speed, which basically says that if CFL is less than or equal to 1, then that geometric property up here, that you're not going further in space than you are in time, will hold. And having CFL, it depends on what you're doing, on how you choose your CFL largely. doing binary black holes or the plane waves that we've been doing, anything around 0.2 or 0.5 would suffice. You can also, if you have a complicated system, you can work out the time-dependent speeds. So the speeds might change with time, and then you can have an adaptive time step rather than thinking of A as completely fixed as a constant. You can have an adaptive time step by A changing, CFL being fixed, dx being fixed. That means that dt will in general change with time. CFD simulations like computational fluid dynamics, I do a little bit of that, and I usually use a CFL of 1, whereas the binary black holes or the plane waves usually 0.2, 0.5. So it's highly dependent upon the phenomena that you're simulating. Okay, that's all I wanted to say about that. Now, we were halfway through looking at the ADM equations. So what we wanted to do is we wanted to take the Einstein equations and we wanted to write down what are the evolution and constraint equations, or the representation of those for a given sort of foliation. So what we did is we said that, okay, we had a conormal that was related to the parametrized surfaces of constant time. And what we wanted to do is we wanted essentially to project the Einstein equations to be intrinsic to the surface with conormal or with normal n, and that would give us the constraint equations, and then the other projections will tell us how these data that satisfy the constraint equations propagate away from the surface. So we did that by saying that, okay, we're going to use this as a projection operator, this gamma, which is the 3 metric of the of these time slices. We take the 4-dimensional metric and the tensor product of the conormals. That together gives us the induced 3 metric that is living orthogonal to these normals, or to the this normal direction. And we want to convert all of the 4-dimensional quantities to 3-dimensional quantities intrinsic to these time slices. All right, so in order to do that, when we did that with the Riemann tensor, we found that indeed some information is lost, as you could probably expect. The information of the curvature sort of away from the surface, which you would expect to be the stuff that's lost when you do this projection, is in fact found in the extrinsic curvature. So this was basically looking at normals, neighboring normals going from one slice to the next. If the surface is curved, then these normals are going to be pointing not parallel, but away from each other or towards each other, depending on the type of curvature. And the difference in the normals on the subsequent time slice is related to this extrinsic curvature. So this sort of tells us how the 3 surface is sort of embedded, this foliation is embedded in the 4-dimensional space-time. All right, so I think we got to here yesterday. So all we do is we want to take different projections of the Einstein equations to compute these evolution and constraints. So the first one we do is projecting everything onto the spatial surface, which kills all of the derivatives away from the surface. And that gives us our constraint equations. So these are called the Hamiltonian and the momentum constraints, and these are very common in literature when looking at numerical relativity. So if we had initial data on one surface that satisfied these equations, then they would be a solution of the Einstein equations, at least on that surface. So it remains to look at what happens when we go away from the surface. So we need to introduce, which we haven't done yet, is how we're going to set up our gauge, which is our coordinates and frame. What the most general evolution from one slice to the next are looking at a fixed spatial coordinate. So suppose we had A here that was at some fixed spatial coordinate, and then we go to the next time slice. It may move relative to where it was on the previous one, And in general, if we define a vector t that is a combination of something proportional to the normal of the surfaces and then a shift, which is the beta, that lies within the slices, that shifts it spatially. So you can think of the lapse as being sort of like a how far do you sort of shift in the time direction, and the beta being the shift in the spatial direction. And a combination of these gives you like a general sort of a propagation from one time slice to the next. And in particular, if you had a fixed spatial coordinates, then the alpha, or the lapse, is inherently related to the proper time that occurred along that spatially constant line. So these are very important, these lapse and shift in numerical relativity, and because they basically control how you perceive the space-time, and that was the thing that took quite a while to figure out how to simulate binary black holes. Was how you choose the gauge that doesn't cause issues. So what we do is, when we write down the projection of the Einstein equations in the other directions, and I won't go into this now in too much detail, we end up with equations like this, which are still abstract. We have yet to introduce coordinates. We've introduced a direction. So you can see here that we have derivatives of the extrinsic curvature and the 3 metric. So these are 3-dimensional quantities, and the right-hand sides are also all 3-dimensional quantities, the 3-dimensional Ricci tensor, 3-dimensional energy momentum tensor, and D being the 3-dimensional covariant derivative. So by choosing a frame, a spatial frame within the time slices, they can be extended in time by Lie dragging. So we take a Lie derivative in the direction of t of these spatial frame vectors and say that they are 0. So that's what's called Lie dragging. We can choose the time-like vector to be proportional to this t. That gives us now 4 orthonormal frame vectors. And within this, we can choose the time coordinate to be a parameter along t, and we get the when we now write this out, and again you can choose sort of arbitrary spatial coordinates that are propagated by t, and we have the t as well. So we have all 4 coordinates, all 4 frame vectors. That gives us a way to write these things down in concrete indices now, which I label with the starts with I and j, and you get the following expressions. So in particular, you can see that the shift is really tangential to the time direction, orthogonal to the time direction. And then we get that the 4 metric with this gauge gives us this following form. So yeah, so this is essentially the basis for numerical relativity. This was I assume this was the first sort of system that was really trying to evolve the full nonlinear Einstein equations on the computer. And so we have as variables the 3 metric, the extrinsic curvature. So there's just 2 quantities here, supplemented by the choices for your lapse and shift. And then we have the constraint equations on each surface. So this was the basis, and this still is the basis for a lot of numerical relativity simulations, but it is no longer used because it was found that these equations are not stable for long-term simulations. So, however, the ones that have been developed to fix that problem are based on these equations, so they're still very important. So, like I said, that there is issues of long-term instabilities with the ADM equations. For first-order systems, one can look at the hyperbolicity, which is directly related to the well-posedness of the system. So that is existence uniqueness, and small changes in initial data lead to small changes in the solution, and so on. If you had a first-order system like this, an analysis of this matrix here that that represents essentially how the spatial derivatives look like in your system, leads to the type of hyperbolicity of your system. But ADM is second order in space, so we have these here and other places as well from the Ricci tensor and so on. So the second order in space really doesn't allow a straightforward analysis like that. And I don't know, I think it was the other order, the idea of looking at seeing how your constraints propagate with time is very important, because how your constraints propagate with time, you want your constraints to be as small as possible, which means that your it means that your solution that you have is a more accurate solution. It's satisfying the Einstein equations to a better accuracy. So an analysis of the constraint propagation system is quite important. I was having a look around earlier in the week, and this paper was saying that the BSSN system that I'll talk about in just a minute, which was a way to take the ADM equations, do some transformations, introduce some more variables and so on, and it works better, wasn't actually done by looking at this, but a subsequent analysis showed that indeed the way that they've done this helps with the constraint propagation being sort of minimal, or not as bad as the ADM equation. So it seems to have been done the other way around. So what is the BSSN formulation? It's named after 4 people who I have not put their names down here. I think, yeah, I probably can't remember them all. But basically what it is it's starting with the ADM equations, you can do some transformations and introduce some more variables, and you get a new system that behaves much better. And indeed, the BSSN and a similar system, the Z4, is really standard in the numerical relativity simulations that you've seen. All of the binary black hole simulations, for example, or at least most of them are done with BSSN. And that's, I think, largely due to the fact that we know good choices of the lapse and shift functions that lead to a numerical evolution that is stable up to and beyond the merger. So let me just briefly talk about what the BSSN equations are, and then I would like to talk about some more advanced numerical methods that go into these binary black hole simulations and other codes in general that make them much better than the sort of very rudimentary stuff of these like the plane waves that we've been doing. So firstly, what we do is we introduce this conformal factor, which is of this type with an exponential here. We introduce a new variable phi, and we multiply this by the 3 metric to get a new one, with the requirement that the determinant of this new metric is 1. And doing a decomposition of the extrinsic curvature, we can look at the trace-free part, which is the Aij, and the trace term, which is the K. And basically taking these definitions and shoving them into the ADM equations, you can obtain equations for evolution equations for this phi and for this new 3 metric, which looks like that. Similarly, we can take the evolution equation for the K, and we get 2 equations, one for its trace and one for this trace-free term, this A, which looks quite nasty, and it is not the prettiest. The BSSN system, in my opinion, is certainly not the prettiest system, but it seems to work. So we have this TF here occurring because A is trace-free. So we have that trace-free terms appear on the right-hand side. So all this is doing is you take your, in this case, a rank 2 tensor, and you subtract a third because we're in 3 dimensions, the 3 metric times the trace. So if you contracted this right-hand side with the 3 metric, by definition, the first term would give you an R. The gamma ij contracted with itself would give you the dimension that you're in, because it's essentially the trace of the Kronecker delta, which is 3, which cancels this third, and then that will give you 0. All right, so I don't want to go into this because it's a little bit fluffing around, I've said, but basically what you want to do is you want to try and minimize mixed second order derivatives that appear, because the wave equation, for example, is hyperbolic, and you want to try and have some notion of hyperbolicity in doing all of this, which is a big driver of doing these calculations. So we introduce a very important function that is essentially the conformal connection components here. So this is with the connection with respect to the this new metric, and contracted over to oops, that should be a J there, contracted over the 2 indices, and we get propagation equations for these as well, which again are not very pretty. But this seems to work. So the BSSN equations are a bit more complicated, a bit longer, but they do have much better long-term stability properties. So this is quite different to the system that we're using for the gravitational waves in the labs, in that one there are only 2 PDEs which propagate the gravitational waves. Here there are quite a few more, and the propagation, I think there is about 8. If you do a characteristic analysis on the system in a certain way, you find that I think there are about 17 or 18 variables at the end of the day, and of those, I think there are 7 or 8 pieces of data you have to impose on the boundary. So the boundary analysis is a lot more complicated with the BSSN. The boundary conditions don't really mean anything physical directly, like the gravitational waves in the labs, and people don't really look at boundary conditions because they are quite complicated, especially to impose numerically. So that's the system. What do people choose for the lapse and shift? Well, there's the Bonamasso family of equations, which evolves the lapse as using a derivative. So I think I spoke a little bit yesterday about this SAT method, which is a way of imposing boundary conditions by putting the wanted value inside a derivative rather than just shoving the value in directly. This is sort of a similar thing, that you don't, the alpha is completely free, right? It's fully gauge. So there's no reason why you can't say, well, it satisfies this equation. If you take a time derivative of this, you see that it obeys some sort of wave equation, which is really good because that implies hyperbolicity and good numerical properties. So a standard choice for this is the 1 plus log slicing, which is given by this choice of F here. And when I was in South Africa, I was working with Dennis Polney, who was on the paper that put forward this choice of lapse. And he told me that he got annoyed at some point because it's now so standard that people have stopped citing the paper. So I think you've done very well if a result that you've published is so standard that nobody cites you anymore. Well, that was quite funny. So that is a nice choice for the lapse, and this is primarily for binary black holes. It works very well. The shift is chosen, usually we use these gamma drivers, which is of the following form here, where in particular It's a second order equation that we usually just introduce a new variable that is just dt on b, just to reduce that to two first order equations which are evolved. And again, it's chosen in a way that that leads to a stable evolution. So this is very difficult in general, and it took quite a bit of work to figure these out, I think. All right, so that tells you that, okay, we have a formulation of the Einstein equations that sort of respects this foliation idea. Given data on one spatial slice, we then evolve it with numerical techniques to the next one, and so on. We have a choice of gauge on how we do this slicing. We've modified the equations to make them a bit more stable long term, but they still have quite a few problems. One of them is, like I said before, the boundary conditions. A sort of characteristic style analysis of propagation or data within the system of PDEs is quite nasty. And although constraint preserving boundary conditions have been imposed or have been published, they're not really used in practice. So what you find is because the constraint propagation system as well as the evolution system, there's so many pieces that are propagating independently, it's difficult to make sure that every piece that is propagating in from the constraint system is zero, because if you don't have that as zero, constraint violating terms, which are just combinations of the system variables that don't satisfy the constraints, will propagate in from the boundary and cause the constraints to be violated, which then means that you haven't satisfied the Einstein equations. So what do people do to get around this? Well, they just put the boundaries really, really far away, outside of causal contact of what you're interested in looking at. So that really turns this into an initial value problem rather than initial boundary value problem. And then if you can get away with that, the idea is to just choose your boundary conditions in a way such that your numerical evolution is stable. It doesn't have to satisfy the Einstein equations on the boundary, but as long as it's stable and far enough away, then you should be okay. And there are hacks within code bases like the Einstein toolkit that allow this to be tractable. So things like doing a radial coordinate transformation as you're going far away. So instead of just using a fixed radial grid, for example, you slowly increase the distance between neighboring points because there is not as much dynamics happening the further away you go as opposed to really close to the black holes. So there are ways to get around this, and this is what most people do. And it certainly works because this is the system that is used to obtain gravitational waveforms from these binary black hole systems. But and I'll talk about this in a little bit later, is different formulations that may be better to extract gravitational waves, because gravitational waves are only defined unambiguously on a surface that's called null infinity, which you may have heard of, which means that in order to read off the waveforms that we use to compare to the observations, we need to be very far away from the black holes in what's called the wave zone, which is so far away that you're approximately in flat space-time, and that's where we read off the gravitational radiation that's used for these comparisons to observations. But if we have to be very, very far away to have an extraction sphere to read off the radiation, then the boundaries have to be even further away, so they are outside of causal contact of that extraction sphere. So the problem is made even worse. Okay, so what I wanted now to talk about was some other problems, alternative methods and advanced techniques for these numerical simulations. So nothing in detail. I just wanted to give an overview of some of the really cool things that people have come up with, specifically for binary black hole simulations, but others in general, and also some methods that eliminate these problems that I talked about of the outer boundary for the BSSN equations not being great. So some of the numerical methods that are used in these binary black hole simulations, there are quite a few different ones. And in the Einstein toolkit, each sort of sub-module is called a thorn because it's based on cactus code. So each sort of replaceable piece, like an evolution thorn or a constraint thorn, or in this case, two punctures thorn, is a sort of module that can be, plugged in or plugged or unplugged and another module plugged in to obtain initial data, whatever. It's quite a hassle. It's not straightforward to get just binary black hole initial data, right? Because you're working with a Cartesian grid, which means that the centers of these black holes contain singularities, which can't really be represented on the computer. So you have to basically puncture. It's called two punctures because you excise the singularity. So you have two punctures in your grid. There is the apparent horizon finding algorithms, which I've been playing around with a summer student, looking at where exactly the horizon is for the black holes. And these are very important for tracking the punctures, very important for taking out or for adaptive mesh refinement, which is looking at around the black holes where the most dynamics is happening. You want to have a finer grid, and usually at the simulations that I've run, which is, to be honest, it's not that many. This isn't exactly my area. There was, I think, 5 levels of refinement. So that means that you have an outer grid that might have a dx of say 1, and then the next level is 0.5, and then 0.25, and then 0.125, and so on. So you have all these sort of finer and finer levels of discretization. And it's called adaptive because, of course, your binary black hole is circling each other, and so your grid needs to follow them. So that's what this adaptive mesh refinement is that the mesh is refined adaptively during the simulation. I've mentioned about the boundary conditions. Spectral methods are also very useful. In fact, there is a code base called SPEC, S-P-E-C, which I think is running out of, I'll say, the west coast of the USA. I can't remember exactly. I think is it Caltech? That use spectral methods to evolve these systems, which I'll mention a little bit about, and some very sort of generic questions and techniques of leveraging parallelization to speed up computation, because these computations are incredibly time-consuming and expensive, and if you didn't do parallelization for these sorts of calculations, you would be waiting a very long time. Even leveraging thousands of CPUs or thousands of cores on a high-performance computer facility, you would be you can look at up to a month for a simulation. And also something that is worth considering is the GPU or CPU. So there are some codes that are being ported to GPU at the moment, including we're trying to look at coffee being ported to the GPU. With the larger and larger sort of data being flung around, GPUs can potentially really increase the speed up of these simulations. So I just thought I'd put that in there. Something that's being taken off from data science and so on, perhaps being used towards these numerical evolutions. So I think, firstly, parallelization is extremely important and necessary for these sorts of things. Coffee is also parallelized with MPI, So what does that mean? Well, basically what we want to do is we want to take our grid and we want to split it into a finite number of subgrids. Each of these subgrids is being run on another process. So this is what's called MPI parallelization, and each of these subgrids has its own memory allocation and its own number of cores, and it does its thing independently. And that is very useful. There is, of course, going to be overhead, because what happens, for example, if I wanted to take a spatial derivative using centralized finite differencing at this point, well, centralized finite differencing, I need to know the neighboring points. So if it was second order, just these two. But now this point is, well, either here or here. Its neighbor is not within its subgrid. Okay, so MPI actually stands for message passing interface, right? So there needs to be some communication between the subgrids to let them know required information. So in particular, there is a message passing done to make sure that if this is an internal boundary, which means that there is another grid attached to it that represents the same boundary, they communicate and tell each other some information so they can still do centralized finite differencing. This is usually through ghost points, where the ghost points are filled with the other grid. So if you imagine that this has a little point here that's not evolved, but the data is actually the data of this one here is put here by communication. So that makes things extremely faster if you do this correctly, but also the fact that you can only do this for a finite amount of, we can only split into a certain size of subgrid before the message passing becomes so overwhelming that the computational gain that you get from having so many cores is negated by all this message passing. And also you only have a finite grid size, so you can only split it up into a certain amount of sizes that, for example, the width of your finite differencing operator, the stencil of that, I couldn't do this for a fourth order one because I need 2 points on each side. It wouldn't work. So you can use something called OpenMP, which is multi-threading. So instead of having just one core per process, where we have 4 processes here, what you can do is you could assign 9 cores based on the number of grid points, for example. This, you wouldn't usually use the number of grid points, but in this case, 9, it's reasonable. And to so for each process, you have 9 CPU cores. So when you're doing these computations and you're doing these calculations, they are done on each grid point. Evolving the equations, you need to calculate all of these operations on each grid point. So why don't you send each grid point a thread, and it does it independently on its own core and then comes back. So the OpenMP is a shared process rather than MPI as being separated, and that makes things also much quicker. So all of these code bases, a combination of MPI and OpenMP, are used to really try and speed this up as much as possible. This is a picture I found by Eric, who was one of the developers of the Einstein toolkit, and this is looks like this is of the lapse in a visualized in Visit, which is a post-processing GUI that is tied in with the output of the Einstein toolkit. So whatever data is produced by the Einstein toolkit, Visit knows how to read it in and grab all of the information. So there we have two black holes here, and each of these is the different refinement levels around the black holes. So as the black holes are moving around each other, this grid moves at certain points in time. It'll say, okay, I'm going to check to see whether my grid is really around the black hole. We know where the black hole is because we have an apparent horizon finding algorithm, and it does that and tracks with the black holes. So that's necessary. If you don't do this adaptive mesh refinement, you either have fine enough mesh to recover or to have a stable evolution, but because it's everywhere in your computational domain, not just around the black holes, it'll be so expensive you'll do anything interesting. Alternatively, if you use a coarser grid everywhere, then it'll be unstable near the black holes and it won't work. So this is really key to getting these simulations stable. Right, so in order to be able to represent these black holes, obviously, if it's on a Cartesian grid, there are going to be singularities in the insides of them. So trying to figure out where they are and basically excising them from the computational domain is necessary. So the event horizon is something that is more commonly used, when you're talking about black holes. But this is actually something that is defined non-locally in time. So it's something like if you have a sort of an interior region of the black hole defined by, for each point in that region, a future pointing null geodesic doesn't reach null infinity, something like that. And so in order to do that, you really need information that is not just in a spatial slice, but in time as well to look at these null geodesics. So Penrose, Suzanne mentioned trapped surface in the last talk. It's a closed two surface whose future pointing outgoing null geodesics have negative expansion. So this is basically saying that if you have a congruence of null geodesics that are pointing even outside the black hole, then they're going to converge in the future. So that means they're going to have to meet and come back in. So there's multiple trapped surfaces, of course, and this would form a region, the trapped region inside the black hole. And the apparent horizon is just the outer boundary of this region. So these apparent horizons are hard to find because in order to compute the expansion, or if you know anything about the Newman-Penrose formalism, the divergence, it's called, they're commonly denoted by rho. In order to compute that, you have to set up a frame which is adapted to the surface in order to calculate the rho, because the rho is based upon the frame choice. But you don't have the surface yet to find the frame adapted to it to calculate the rho. So it's a little complicated. Jonathan Thornburg has a very nice review article on all of the different methods to do this, and they have been implemented very well. And so that's very important for these simulations, is knowing exactly where these black holes are. And you know that if you have an apparent horizon, then you know that you can essentially take out anything on the inside, and physically that's not going to do anything to the outside of your black hole. Numerically it might, but physically no. Some other interesting things I think are pseudospectral methods. So these I use these all the time, and the work with Jörg Fraundiner, we have implemented these and use these for angular representations of functions. So basically what it is if you have a function that is, for example, defined on some spherical surface, then there is a basis for that function. In general, these are called spin-weighted spherical harmonics, where you just have a series, and this series has constant coefficients here, these SALMs, and these are complex and constant in general. And what you find is as you have more and more of these terms, just like the Fourier series, you should see, if this is well represented, that these coefficients should drop away to zero very quickly. And so this series is truncated at some L, otherwise this would be infinity. So this should really be an approximation here. So the really nice thing about these pseudospectral methods is that you can take some function, you can write it in terms of the spin-weighted spherical harmonic basis, where the coefficients are given by integrating over the sphere, weighted by your function with the spherical harmonics. And once you've got these coefficients, then it's very nice to take derivatives or to do interpolation, because suppose you've done this integration, which is always numerical in practice, then if my function is represented like this, how do I take a derivative? Well, if I took a derivative on the sphere, then the only thing is that these SYLMs are functions on the sphere. So the derivative can come in, go through the constant spectral coefficients and act on this. And the SYLMs are known analytically. So we know what the derivative is analytically. So we can very easily take derivatives once we know the spectral coefficients. So this is called semi-analytic, because in order to know the coefficients, we have to do this integral, which is usually done numerically. Further, if we wanted to know f evaluated at theta or phi, no matter what value, we just plug it into the basis functions and we get our interpolation there. And so this is quite different from taking derivatives using finite differences, which is something that's sort of local around a particular point. But these spectral methods are global in some sense, because in order to calculate them, you're taking integrals over the entire spherical domain here. So they eliminate problems like the Gibbs phenomenon, for example, which is sort of errors that occur close to the boundaries. This is one way of avoiding those errors. So these are extremely useful, and they can be extremely fast as well. So I thought I would have to mention these. And I think I have just enough time to go through a couple of other formulations of the Einstein equations for numerical evolutions that I've played around with, that I think, if they work, would be very nice compared to BSSM. So the first one is the one that you have been playing around with in the lab, which is the Friedrich-Nagy initial boundary value problem for the Einstein equations. So this was presented in 1999, and it was the first well-posed IBVP. However, it uses the Newman-Penrose formalism, and it was deemed too complicated, and no one implemented it, or at least implemented it successfully on the computer. And Jürg and I implemented it nearly a decade ago in plane symmetry, which is the system that you've been playing with, which seems to work very nicely. So in particular here, the major difference between this and BSSN is it's very easy to impose boundary conditions while still satisfying the constraint equations. So as you could see, when you did your convergence plots yesterday, there was no issues. You could see nice convergence, and you had a boundary condition that represented this bump coming in, no problems. So this, the nice properties of the system is essentially utilizing the Bianchi subsystem of the Newman-Penrose formalism. So you might know that there is this Bianchi identity, whichever number it is, that the covariant derivative of the Riemann tensor is 0 when anti-symmetrized over, I think, the first three indices, including the derivative. That subsystem, or the system arising from that identity gives rise to a symmetric hyperbolic system for the curvature, or for the curvature coming from, in this case, the Weyl curvature of the Weyl tensor, because the Ricci contribution is 0 in vacuum. And so symmetric hyperbolic is the top tier hyperbolic classification you can have, and that means that it is really well posed and you have really nice properties before you start even touching a computer. So this is a very nice system, and I feel like this has prospects in the future because it is able to look at gravitational waves in a reasonably arbitrary setting. It's non-linear, and you can choose the boundary conditions to essentially generate gravitational waves as you please. Whereas with BSSN, you cannot generate dynamics through the boundaries because there is all of that complicated propagation of data and so on happening there. And it's also very difficult if you wanted to then use an initial surface to generate dynamics, because that means you would have to solve non-trivial constraint equations, which are elliptic, completely different numerical techniques to do that, and that is very difficult. So that's my plug for the Friedrich-Nagy gauge anyway. Another one that I wanted to just mention in the last sort of 5 minutes is how do we measure this gravitational radiation? So like I mentioned briefly before, there is this null surface somewhere that is not within the computational domain. This is a surface that represents the endpoints of null geodesics in what's called an asymptotically flat space-time. So what this is, it's sort of an ideal surface that is not included in the physical domain, but that is in fact mathematically where these gravitational waves are well defined. We're not incorporating that into the physical Einstein equations and BSSN or so on, so we never actually get there. So that's kind of not the best start. Instead, we have some outer boundary here, which is time-like. We have to truncate it at some point. We can't go all the way to infinity. And this time-like outer boundary tends towards a point in the future that is not on this surface. So we cannot ever get to Scri plus with the physical Einstein equations. But we can approximate it. So what we can say is, well, if we go far enough away such that, you know, we're in a region where space-time is roughly flat and so on, and it's close enough to being at null infinity that we can do it, we can look at extracting gravitational radiation here. But we have to be careful that with these BSSN equations, we have to move this outer boundary outside of causal contact of this extraction sphere. So that's not the best way of doing it. One alternative, well, I should mention here as well, this is just a little picture showing that over time, these constraint violating modes will propagate in from the boundary and destroy convergence on your extraction sphere. So if this was your simulation and the red corresponded to these violating modes, you would have to move your outer boundary even further away. So one way to do it, another way, is called Cauchy characteristic extraction, which is a really nice concept of utilizing null foliation. So instead of us having this spatial slices of constant time, we have null slices. And the advantage of this procedure is indeed that these null slices can go all the way to null infinity, and we can read off the gravitational information directly from there. So this Cauchy characteristic, Cauchy meaning the spatial slices, characteristic meaning the null slices, suppose in fact that you did a standard evolution, but you saved data on some world tube somewhere in your computational domain, and then you stopped and you said, okay, I'm going to then start with this world tube data, integrate my equations out to this null infinity surface and obtain data there, do a little evolution and continue. I don't want to go into too much detail, but this gives you a way of getting out to Scri, giving some seed values on the world tube plus one. There is one function here on the null slices that's evolved between them. So this is based on the Bondi-Sachs formalism, which is a formulation of the a coordinate system or a gauge that was used in the 60s by Bondi, Metzner, and Sachs, and all of these people that were looking really hard at asymptotic properties of these systems and how to unambiguously define gravitational radiation and all of these things. And this resulted in the Bondi-Sachs mass loss. So this is something that has been successfully done by a group, Nigel Bishop, Dennis Polney, and Christian Reiswig, in the sort of late 2000s. One thing that hasn't been done is Cauchy characteristic matching. So the problem with the extraction is you still had this outer boundary. What matching does is it completely eliminates that by matching these two completely different ways of evolving the Einstein equations at some common world tube or some boundary, some interface between them. And this has never been done, and I've spent quite a bit of time on it. Still doesn't work, but it is a really nice concept in that the code, the characteristic code is extremely fast. It gets all the way to null infinity where gravitational waves are unambiguously defined, and it avoids having to worry about boundary conditions for BSSN, because the boundary conditions that satisfy the Einstein equations are given for free by knowing data on this characteristic side. So this information exchange both ways is called Cauchy characteristic matching. So it's never worked even in 1+1. Will it ever work? Well, Jörg doesn't think so, but we will see at least, or maybe just not see whether this will work. But there are some methods around that may be better for doing these binary black hole evolutions that haven't been implemented yet. So I think that is pretty much my time. I'll leave it there, and I'm happy to answer questions, or now I need to go and have a look to see if the labs are be able to be run, if the virtual machine is up and running again.
Okay, thank you, Chris. Well, you think I'm so pessimistic? I'm not sure. I think there are better formulations around. But anyway, are there any questions? There was a question in the chat earlier that I saw. Yep. So question to Chris about yesterday's talk. When we foliate space-time into spatial slices of constant t, we are making a choice of coordinates, right? Is there any conventional choice that helps our computation? And what are the observer-independent quantities we can calculate from this choice?
Yeah, so I mean, the choice of t is intimately related to the lapse function, right? So this is basically the coefficient in the dt squared that tells you how you go, how fast time propagates with respect to your coordinate system. So what are the observer independent quantities? Well, this is all gauge, right? So this is something that's not well, this is something that doesn't depend on an observer in some sense, but what I'm talking about in the lab today, as long as it happens, is what's called scalar curvature invariance. So this is something very important from an observer point of view, in that you want something physical in your space-time. You know, you have a quantity and you want to know, oh, if this quantity goes bad, is that because of my choice of coordinates, like, the lapse and shift are a choice of your gauge, or is it something physical that's going bad? And the scalar curvature invariants are a way of analyzing curvature, such as probing singularities or something like the event horizon of a black hole, which is independent of the choice of frame. So the Kretschmann scalar is a famous one, which is just the 4 index Riemann tensor contracted with a 4 index Riemann tensor, which gives you a scalar. Because it's a complete contraction, it's independent of your frame, and so it represents some notion of physical curvature. And that when evaluated in the Schwarzschild spacetime, for example, is fine at the event horizon, which is known to be just a coordinate singularity, but in fact at r equals 0, it still blows up. So things like this are very useful to understand whether bad things are happening. Is that a physical feature of your space-time, or is it a artifact of a bad choice of gauge, for example?
Right. Any other questions? I don't see anything. So then I'll suggest that you check out, Chris, what the VM is doing, and we'll reconvene in maybe 15 minutes. So that's 10 to 4.
Oh, that sounds good. Thank you.